Hello everyone and welcome. Today we're gonna see some essential concepts of lambda calculus, alpha equivalence, alpha conversion, and beta reduction. These are key ideas in understanding how we manipulate and evaluate lambda terms. Let's break them down. Firstly, let's see what a bound variable is, because we will need this in the definition of alpha equivalence. A bound variable is a variable x which is bound by the symbol lambda x, called its binder. Basically, it's a placeholder whose meaning only exists inside that function. A variable which is not bound is called free. Everyone is probably already used to the following habit. When working with a function, such as f of x equals x cubed plus 2, we can all agree that the choice of the variable x is completely arbitrary. If we wrote the function as t cubed plus 2 or f of z is equal to z cubed plus 2, it would have not changed its meaning. This is precisely the idea behind alpha equivalence. In lambda calculus, terms can look different but still represent the same thing, i.e. the same semantics, the same behavior. Imagine we have the following lambda term, lambda x, which maps x to x. Now we can replace the bound variable x with another variable, such as y, and we can write it as lambda y dot y. So lambda x dot x is alpha equivalent to lambda y dot y. The general rule is that lambda x dot m, where m is any expression, is alpha equivalent to lambda y m, which this notation here x slash y means that we're gonna replace all the instances of x inside of m with y. Closely tied to alpha equivalence is alpha conversion. Alpha conversion is the process of renaming bound variables in a term to make it more convenient, while ensuring the meaning of the term stays the same. Let's take an example. For example, the term lambda x dot x plus y, here as we can see, x is bound and y is a free variable. Now we can convert the bound variable x and rename it as, for example, t. And now the expression we have is lambda t dot t plus y, which is exactly the same. This is just renaming, it's not a change of meaning. Now let's get into beta reduction. This is the process of simplifying lambda terms by applying a function to an argument. Imagine the term lambda x dot x with 2 outside. Now, lambda x dot x is a function that takes x and returns x itself. So when we apply that to 2, we can reduce the term by substituting x with 2, which just yields 2. In terms of notation, we write this as lambda x dot x 2 beta reduces to 2. And this step is called beta reduction. Essentially, we're reducing the term by applying the function to its argument. This is, however, an intuitive definition, and we just defined it, we could say, bottom-up, by just providing an example and then explaining how that was a sort of an instance of a thing. But formally, beta reduction is defined as follows. So if we have a function, lambda x dot e, and apply it to z, then we can beta reduce it to e z slash x, which means we are replacing all the free occurrences of x in e with z. Now let's see how beta reduction works with a more complex example. Consider the following application. So the function lambda x dot y, which maps x to y, y is a free variable, applied to lambda z dot z, where this is a function which maps essentially a value to itself. In this case, the first function doesn't even use x. So after applying it to lambda z dot z, it simply returns y, no matter what the argument is. So we reduce lambda x dot y applied to lambda z dot z to just y. And this is a simple application of beta reduction, where the argument doesn't affect the result. After performing beta reduction, we often want to know when a term reaches its simplest form, which it's called normal form. A term is in normal form if no further reductions can be made. Let's look at the term lambda x dot x applied to 2. We can reduce it to 2, and since there are no more reductions we can make, 2 is the normal form of the term. Now, to sum up, we have seen alpha equivalence, which lets us say that two terms are the same if the bound variables are named, as long as no free variables are affected. Alpha conversion is the act of renaming bound variables without changing the term's meaning. And beta reduction is the process of simplifying lambda terms by applying functions to their arguments until we reach the simplest form, known as the normal form. As we said in the last video, we use beta reduction in the proofs for showing certain relations for the beta encodings of logical operators. And in this video, we showed what actually beta reduction is. So now the viewer can see how and more formally what we did in the proofs of the last video. Understanding this concept is crucial when working with functional programming and formal logic. These transformations, in fact, are the foundation for how we manipulate and evaluate functions in lambda calculus. With this said, I thank you for watching and happy calculating.